Hello everyone, welcome to production readiness testing using Apache Spark. So my name is Jag and we also have Ganesh here. So we are going to talk about three parts in this talk. So the first talk is like a 2-minute brief background into the Salesforce App Cloud and also the Apex programming language. The second part is going to be like the challenges involved in testing these. So we have a process called as the hammer, which is the last round of testing that we do before we release it to the customers. So we are going to talk about the challenges. That's the second part, and the last and final part is going to be how we use Spark to help us with this. To start with, right? So Salesforce App Cloud is a bundle of these services. We have the Force.com, Lightning, Heroku, and a few others. So we're going to primarily focus on the Force.com. So which is a platform as a service offering that allows our customers to create custom applications that reside on the Salesforce infrastructure. So in order to do that, our customers use a programming language called Apex. So this is a Salesforce proprietary programming language, which is very similar to Java. It is strongly typed, object oriented, and in addition to that, we do provide like a IDE on the Salesforce.com that people can use, and in addition to that, it's really simple to write unit tests and test your code right there in the IDE. So one thing is like we do expect people to have like a minimum of 75% of automated test coverage before they actually check in their code, and those tests are going to help us with the actual hammer process, which is also called as the production readiness testing. So with this, I hand it over to Ganesh, who's going to take it us from here.
Thank you, Jack. Hello, good morning, everyone. So let's quickly start up with what is the hammer process, what is readiness, production readiness. Salesforce makes 3 releases every year, the platform of service offering. And few weeks before each release, we have exhaustive testing going on the entire platform. And as a part of that, what we have known as the production readiness test, internally we call it as a hammer process. And what we do in the production readiness testing or the hammer process is that we take all the tests that our customers have written, 150 million of them, and run them twice. First time when we run it on the current production versions that we have in our data centers and collect all the results. And the second execution, what we call it is the upgraded run. This is the version that is, the second run happens on the candidate version of the software, which is going to be released in a few weeks' time. And we collect the results of that execution. And eventually, and then compare the results of both and see what's going on with the 2 results. The upgraded and the baseline run are compared. When test passes in the current version, it is expected to pass in the future version that is going to come up as well. And if the test was failing, it is expected to fail in the future version of the software as well. And any other outcome is a potential regression that we may be introducing in the upcoming version of the software release. And that is what the hammer process is going to identify that. When the hammer process is finished, what we have is a bunch of clusters that are generated. And what you see at the bottom of your screen, right bottom, there are a bunch of clusters. And each cluster is a group of similar looking test failure messages. And how we generate this cluster and what these clusters mean, we're going to learn in subsequent slides. So this was a quick introduction to the production readiness testing. So before we go into the actual solution itself, we needed to understand what are the challenges and magnitude of complexity of the challenges we went through. So the biggest challenge what we have is 150 million tests that customers have written. And this number is growing and it is expected to grow in upcoming releases as well. And the whole operation is infrastructure intensive. We have to have a huge amount of infrastructure dedicated for this, which involves large number of team working across geography to set up this infrastructure and make sure that the hammer processes are able to run in our production data centers. And once the results are there, we need to persist them and compare these 2 results. And that has some complex computations there. And then tests are executed highly secured environment, which means since it's a customer production test and we do not have any access to any data or output results whatsoever, which makes this very harder. Which makes it very harder for us to see what's in the test and why the tests are failing. So we only look at the test failure result as such. I just move forward. Sorry. All right. So after this, let's have a quick look at the functional overview of the solution, what we came up with. And as typical with any data processing software, the first step is the data ingestion. We have all our data in the data centers that we need to somehow pull it into our cluster where all the computation is to happen. And we have some secured APIs through which we download all this data into the Hammer infrastructure where we do all the computations. And second stage is the ETL step, where we extensively use Spark SQL and data frames to do this computing. Basically, this step is where you're going to refine the data, remove all the noise, and then make sure that the data is high quality for further analysis using the machine learning algorithms. And at this stage, we are going to probably clean up 80% of the data that we receive from our data centers. And the third stage is the clustering. We're going to talk more about this in a subsequent slide, which is basically look at all the optimized data and run through the machine learning algorithms, which can classify or cluster the results together and say these clusters could be a potential bug which you need to further analysis. And output of that is, again, the bunch of clusters. Each cluster can represent a potential bug in the future software. All right, so with that, let's get a little bit detailed into architecture, how the architecture looks, and what are the software stack that we have been using here. The Hammer infrastructure is built on Hadoop, Apache Hadoop platform. We use HBase for data store, and Spark is our data processing engine. And top of Spark, what we have is a Hammer core. And Hammer core is nothing but a bunch of Hammer business rules, which are written in either Java, or in some cases in Scala, that extensively use Spark APIs across different libraries, from Spark SQL to Spark ML. And as we just saw, that the data into the Hammer core are being pulled from the secured API from our data center. And then we do have a small UI in a web server, which allows us for a manual investigation of the cluster. And we use Apache Phoenix, which is a Salesforce contribution to the Apache projects, and which allows us to, the Phoenix has a very fast and queries to run on HBase. We do some analytics with the Phoenix queries on HBase data for presentation and manual analysis perspective. So this is how the architecture looks like. So let's, after this, the next question comes in, what are the test failures? What do we actually analyze here? So in order to understand, we need to take a look at the data preparation stage, which is ETL, where we extensively use Apache Spark SQL. And let's have a look at the sample execution of a test. So when you say a unit test, what do we generally do is a unit test, we have certain assertion. Expected this, and actual is this. And if the assertion holds true, the test pass. And if assertion holds false, then the test fails. Or assertion fails, the test fails. So let's have a look at the example on your screen here. We have a result of two test execution. The first execution is a baseline. It's the output of the test execution on the currently production software. And it's a simple scenario here, where the test output says expected 10 and actual 10. Obviously, the test is passed. And the same test, when it was run on the upgraded version or the future version of the Salesforce software, the test again passes, expected 10, actual 10. And this is a good, happy scenario for us. And the Spark SQL transformation picks it up, which we call it a pass-pass transformation, and tags such test results as not a bug. And these are not a bug. We don't have to worry about them. All is good here. So the second example here is another happy case scenario where we have a baseline execution of test. There is some null pointer exception. So obviously, the test has failed. But when the same test, when we run it on the future version of the software in upgraded run, the test failed for the same reason again. So it is a fail scenario, and we have the Spark transformation called FF is going to pick this up and mark it as not a bug. So here, it's an expected scenario. If the test was failing in the production version and it's going to fail in the future of the software, we are OK. It's not a problem for us, and we don't have to worry about this. The third scenario is where it gets a little bit interesting. We have a baseline execution where a test is making an assertion, expected 10, and actual is 10. So the test has passed. But what happened the same test on the upgraded version is that there is an exception being thrown, null pointer exception, so which is a fail. So we have a scenario here where a test execution passed in the current production version, and it is failing in the future candidate version of the release software, which indicates that we may be introducing a regression in our future software, and such kind of a failures require further examination. And we have a transformation that called pass-fail scenario, which picks up such tests and marks them as for further analysis. And these are the tests that are going to be analyzed in the subsequent stages of our algorithms to classify and cluster and see what's going on with this test and why they are failing. And it will want some manual investigation from some engineers to see why the test was failing. So let's look at the final scenario here. The baseline is expected 10, and the actual was 21. So which means that their assertion is failing because the expected is something and actually is something else. So there is a failure in the baseline. That's fine. And what happened to that test in the upgrade? So the upgrade, the expected is 10 again, but the actual is 51. So you see the test is failing in the upgrade version as well, but the failure is for a different reason. And this is a category of test, the transformation we call as fail, fail, dash. It was failing earlier, but it is failing now for a different reason. So this is, again, a potential regression that we may want to take a deeper look into to see what's going on, why the test is failing for a different reason. And the transformation appropriately marks them as further analysis. Now, these are the few simple examples of ETL stages that we use Spark SQL to do a lot of filtering and cleaning up data. There are other complicated cleaning up mechanisms as well, where normalization of the IDs and the dates, etc. So after all this stage, the data goes to the next stage, where we have a clustering algorithm to churn through the cleaned up data, which my colleague Jag is going to walk you through further. Thank you.
Thanks, Ganesh. So just to reiterate, right? So we now have all the tests that need to be analyzed, analyzed as marked as for further analysis. And the goal of the machine learning pipeline that we have built is to group these test failures into like k different clusters. The idea is like each of these clusters should ideally represent one potential bug in the platform, one regression that we have introduced. And we also want to like provide an easy way for our engineers to go and determine if such a cluster is a bug or not, and if it is a bug, assign it to the appropriate team. So that's the overall goal for the Spark ML pipeline. So let's see how we built it. So the very first transformation. First of all, the Spark ML pipeline is built using several transformations. So each one is a transformer, and it takes in a Spark data frame and outputs another data frame, a transformed version of that data frame. So our very first transformation is the filter transformer. What it does is it goes to our HDFS store and then just picks up those test results that are marked as for further analysis, and loads it up in a data frame, and then it's ready for the next transformation, which is a tokenizer transformation. So tokenizer transformation is what it does is it looks at the error message and then splits that into an array of strings. So in this case, you can see that system.dml exception, insert, failed, all those became separate strings on their own. In addition, it like truncates trailing spaces or like special characters. So this is called as a bag of word approach, where all we have done is like picked up those words and then assigned into simple arrays. So when we first attempted a spike on this, we did try the other approaches like the bigram and trigram, but finally we settled with the bag of words approach because that seemed to give us the best performance. It also, what it means is like in theory, the sequence of these words in the exception messages do not really add value to our analysis. That's what it means. The next thing, right, it's the stop words removal transformation. So once we have these messages, we want to like filter out messages that will not add value to our analysis. So stop words are common English language words like say the, on, and so on. So in this case, in this example, you could see that on, that's a word that's a too common word. We really don't want that for further analysis. So that is removed. Spark ships with a built-in list of stop words. So we just went ahead and used that. The next one is called the canonicalizer transformation. So what that does is like, it's very similar to the stop words removal. What it does is like, we just group common data and then we give it a normalized tag. So in this case, you can see date. We actually do it for multiple versions of date in different formats as well, and then tag them as like with this custom tag, which is date. We also do that for a few other Salesforce specific IDs, say for example the customer ID, for example. Once that is done, our arrays go through the TF calculator, which is a term frequency calculator. So term frequency is calculating the frequency of a word in a given document. So in this case, it's going to be the document is just the array of strings, and we are going to like compute how often they have occurred in this particular array. So what you have here as the output of the term frequency calculator transformation is a sparse vector. So what you have, the 100, 101, 123, those things are the hashed values for those strings, where the hash space is actually every single unique word in the overall error space that we have. So you take the list of all the error messages and then compute the unique words. That's the hash space we are talking about, and then and that's going to influence the hash key here, like 100, 101, and 201. And the second part is the frequency at which they have occurred. So you have like system.dml exception has occurred just once, whereas insert, you see it's occurred twice, and then you see right there. So sparse vector format is one of the preferred formats in our scenario, mainly because like the number of features that we had was like way too many, and then they were very sparsely represented. What I mean by that is like, so we say for example we had like say a 5,000 length array, but we had values only for like say 4 or 5 of them. So instead of just adding like zeros to all of the rest of the values, you could ideally represent them as a sparse vector. Once we have the sparse vector, what we have essentially done is we took an error message and then we now reduced it into a numeric array. So just remember that this, for the sake of explanation, we are just doing this for one particular error message. In reality, we are talking about like hundreds of thousands or even like millions of such error messages. And once we do that, we just pass it on to a k-means clustering. So we are using the Spark ML k-means clustering, and what we want as an output of that is we want these error messages to be grouped into say k number of clusters, where each one of those clusters uniquely represents a bug, as we mentioned. So, and what we provide using the UI tier, which Ganesh talked about, is like an easy way for our engineers to go and look into each of these clusters and then make sure that they actually are a bug or not a bug. And if they are a bug, we have an in-house technology where, looking at the stack trace, it's really simple to like find out which Scrum team to assign the bug to, and that is taken care automatically. So now let's look at the accomplishments. So on the ETL side, so Spark was a clear winner. So compared to our old Hammer engine, so let's take the example of the second row. So where we had like the number of test records to analyze was like about 500,000, more than 500,000, and then the old Hammer analyzer took us like 7.8 hours. So just to be sure, the second column is in hours, and the third one with Spark is in minutes. So you can see it's from close to 8 hours, we brought it down to like 13 minutes, and that's a speed improvement of about 97%. So this is super critical for us because we want to like get the entire Hammer analysis done in less than 3 weeks. So that's where Spark really helped us with improving the speed. We saw that across pretty much all bunches of test results. Like Spark was clear winner in every single scenario. Next, let's look at the clustering phase of it. So for the clusters, right, our old analyzer used a regular expression based one, where it'll look into the test failures, and then we have a set of regular expressions, and it'll try to match it. When we compared the results with that, right, there were far fewer clusters to analyze with the Spark ML k-means. And the second thing is like each clusters was very well formed. What I mean by that is like each cluster ideally represented just one regression, That's the ideal case scenario. In most cases, we could do that. And the quality of the bugs that we filed based out of this was also far better than our old regular expression based one. And speed, definitely once again Spark is a winner. So to do clustering on about say 100K plus records with like several thousands of features, it took us like about 40 minutes to complete that. And whereas the old one used to take us like several hours. With that, I'll open it up for Q&A. Thank you. Yes, right there.
Sorry, can you raise your hand a bit higher? All right. So the data are going to be piped into the k-means, and how do you decide how many clusters you're going to choose? And
sure, yeah, great question. So that's the value of k. So the value of k is decided based on our past experience, looking at how many bugs we have filed in the past releases. And then since so the very first time we released, we did a testing with both the old analyzer and the new analyzer. And with the old analyzer, we know that what is the expected value of k, and then we tune the k based on that. So in short, it's mostly learned from our past experience.
In your pipeline, so how many number of features did you set for the hashing TF transformer, and how does it affect the performance of k-means?
Sure.
So just want to
Yeah.
see your experience.
Sounds good. So the latest version used about close to 6,000 features. So the entire vector space you're talking about, like say 6,000 features, and then the total count is like about a few 100,000. So yeah, we did do some dimension redactionality, so to bring it down to 5,000. So we are not included that as part of the talk. Yeah, right there.
Thanks for the presentation. Given that after each run, each cluster would be matched or related to a single bug or a single problem, do you take the content of that cluster then, and train a supervised learning classifier instead of a clustering technique? Because now you know what is the problem related to that cluster, and the data in that cluster now represent kind of a training data or actual training data, because you know that they have that problem.
Right.
Does it make sense then to, instead of keep doing clustering all the time, after some time, since you have enough number of training data and enough number of bugs that you discover, you train a classifier instead of clustering, because supervised learning is always much better and accurate than the unsupervised learning?
Sure. So at this moment, we are not doing that, but I think that's a great point. So the main reason why we are not doing that is because the kind of errors we get is far different with every release, because there are like just several teams that are going to check in, and then the way they log the error messages and the stack traces are fairly different every release. But we have a few other ideas on how we should do it, but we are not there yet. Yeah, but I agree to your point. At some point, we'll have to move away from the unsupervised to the supervised world.
Hi, I was just curious, when you were comparing sort of your previous engine to your current engine with Spark, what exactly was the setup in the old engine? I guess what enabled you to make such gains other than Spark, you know?
Sure. So do you want to take it, Ganesh?
Sorry, could you repeat the question,
so
please?
It's okay. So let me take that.
Okay.
So the idea is like so the old one is a Java based one. It's not a MapReduce one. So we figured out that that's not scaling, and then we wanted a more parallel solution, and then we did a spike at both MapReduce and Spark. So for MapReduce, we used like a Mahout for the ML part, and for Spark we used the Spark ML part, and then Spark ML was a clear winner in every single use case that we could try, and eventually we picked.
Just to add to that point, it was also significantly important for at that time when we were doing a spike, we were not sure the deployment environment, how it is going to be. We were not sure about the infrastructure that is going to be available to us. So we wanted to choose a technology that would keep us free unbind it from the underlying infrastructure that we are going to use. And Spark was a clear winner where it can run on many different platforms, where if you use the Apache MapReduce, we are kind of bound to HDFS and the related technologies. So that's why we actually chose MapReduce, or chose Spark over MapReduce. There's one gentleman here, last question.
Thank you. So do you think this model can actually be applied to maybe a company that has like a continuous release process and do more of a real-time analysis than doing batch approaches? Do you see a use case for that?
Sure. So I'm just trying to see at what point during the continuous deployment process you would be continuously running tests. So yes, we could see, okay, I could think of a scenario where, say, the test results are coming in batches, and then you want to like really do it as part of continuous thing rather than like batching it. Yes, I think we have plans to replace our first step of ETL from a batch to a streamed one. So that is also in our pipeline. We haven't done that yet. But yes, once we do that, definitely I think that should be possible for the use case that you're talking about, where things are arriving in sequence, and then you want to do things in real time.
Yeah. Probably the last question from there.
Great presentation. So a couple of follow-on questions that were asked earlier. So how did you guys deal with the stochastic reproducibility of your clusters? And also, I think you guys were using hashing. How did you guys double check if there's any collisions from the hashing?
Okay, so can you repeat the first question?
So the first question is asking the reproducibility of your clusters.
Okay.
And then the second is the hash collisions.
Sounds good, yeah. So, so k-means by itself, you cannot reproduce it, mainly because the centroids that we are picking, they are picked up at random, so we just leave it up to the Spark ML k-means to pick up the initial clusters. So there is always some vagueness in the cluster with every run. So there is no way out of it if you're doing unsupervised learning. So I think we'll have to live with that. For your second part, right, I think the hash could result in collisions, but for the scale that we are talking about, right, I think that's a fair enough noise that we could ignore. So we have been able to get away with that way, yeah. So we are not we don't spend like take any additional efforts to make sure there is no collision.
Thank you.
Thank you.